the project I did a couple of years ago with Núria Fagella and Xavier Jarque at the University of Barcelona. And Clara and Juan have also seen these results, but I'm going to talk about that today. So I'm just recycling the same talk I was planning last year. So let's see. I'd like to start with this picture as a metaphor for this quote from William Thurston. Mathematics is a process of starting hard enough at the fog of confusion to eventually break through to improve the clarity. I took this quote from Thurston's profile in Math Overflow. He was a big user of that platform, asking many questions and interacting with users there. And when he was doing this kind of research back in 2008, I was working at Heidelberg University in an interactive website with a numerical research group in geometry. But I was working mainly in fractal trees, and there was one special map that was related to this picture he published a few years later. And I'm mentioning that because there is also this nice citation in the paper with Alceda, Libra, and Mizrevich. And that's an interesting book, but I'm not going to be talking about that. I'm going to be talking about this fractal tree perspective. And thanks to that paper, now there is some interest in the holomorphic dynamics community about studying this kind of maps. And there is this nice paper by Sarah Koch and Danny Caligari and Alton Walker. And that's the reason why, like 3 years ago, I contacted Núria Fagella and his group, and the group at UV. And I'm going to be explaining the insights I got by using this notion of tree structures and looking at these maps. So the notion of complex tree is about generalizing the geometric series. Is when you, for example, if you take like 2 complex numbers, that's going to be your alphabet, and then all the possible combinatorial possibilities are going to give you the nodes and the T points eventually. So let's see, for example, a binary alphabet. From that, you start constructing some finite words, and by geometric map, I'm mapping these finite words to nodes of the tree. So for example, 1, 1 is this node, and then 1, 1, 2, ending in red is this other node. So you can have all the nodes mapped by finite words. The empty string is always mapped at 1, and then that's this what I call the nodes of the tree in yellow. But then if your word is made out of infinite letters, then you have T points. So that's a typical example of the just 1, 1, 1, that you have this closed form for the geometric series. You can take the C2 letter, and then you get this other node there, but then you can also have for periodic words or eventually periodic, then you have these closed forms that you can find the nodes in there. So the tip set is the set of all these infinite strings mapped to the complex plane. And you can see that that's a self-similar set because it's composed of 2 linear maps. And for example, the map F2 is just like contracting by the complex letter C2 and adding the rotation by the argument of that complex number. And then I'm adding this one translation is +1. You can do the same for the F1, and the union of these 2 transformations is what you get as the invariant set of the self-similar set. In this case, the red piece F2 and the black piece F1 is disconnected, and that's a way to prove that it's a Cantor-like set. But what I got is that you can like impose to glue different T points together, and that's going to give you some examples of connected self-similar sets. So let's see one example. I'm taking these 2 pairs of T points and imposing them that's like the closest expressions, but I'm imposing them to be connected. And you get a system of 2 equations with 3 non-complex numbers, and you can find out that's the parameterization that gives you a solution. when this red branch is always going to stay at 1/2. And then the parameter is like the black is related to the black branch. So as you move that, you're going to be moving the blue branch according to this function 1/4z. So that's giving you the parameterization of the family. And for this value of z, you get that the tree is only connected in these 2 points, like the F1 and F2 intersection only in D, and then F2 and F3 are intersecting only in this point E. So because you are like only having these 2 pairs of tip points, that's how I define what I call the topological set of the tree. And now you can move around an epsilon neighborhood, and as you are like perturbating that initial value, you're going to have like a self-similar set that is structurally homeomorphic to the original one. So this what I call the structurally stable trees, when you are having only these 2 conditions that are connected in these 2 ways. So let's see that family is defined in an anomalous, because you want all the 3 branches to be smaller than 1, and that happens for the blue branch happens when that's the modulus is bigger than 1/4. So that you have to remove this part, and that's why the family is defined in this anomalous. The example I was showing at the beginning was this point in white, and that's giving you this tip set. And I'm gonna just move around this parameter space by picking different z values. And you can see that the geometry is changing, but the topological set is staying the same. You only have these 2 points of contact. And now I'm gonna be moving a bit left. And eventually you get that now the piece in black and the piece in blue is intersecting. And that's happening when you have these 2 pair of tip points intersecting there. And now your topological set has changed. You have to add this relation additionally. So when that happens in your parameter space, I color that point in black. And that was for the case of the Sierpinski triangle, when you get this particular value. But you can find other black points in the parameter space by defining these, imposing these tip conditions. And for example, if you add this condition, then you have a polynomial and you can find the root. And when you find the root, you add the point. So that's this example when you get this element. But then you have other solutions when you impose different tip conditions. And you're gonna start like doing that in the computer and find a lot of different combinatorial possibilities, starting with 1 and 3 or 1 in 2. And then you have this map that I'm showing in the picture. That is an approximation of the final set of non-stable trees. So the stable ones are these white regions. That's one I was moving at the beginning. But as soon as you cross to the black region, you have more tip points that are connected. So I was able to prove that for this particular family, you get a piecewise smooth boundary. And that's defined by these direct curves. But then I'm going to skip the proof and the details, but you have the idea that when you're like moving around this boundary, the deep sets are only just touching. You have the initial deep points connected, but then you have some other initial parts that are connected as well. So that's another part, and I'm showing here the different colors because you have these Mobius transformations that are mapping the blue region there to this other region in there, but it's because of the symmetry of the family I'm showing here. So the critical points are these landmarks, and you get small direct numbers in these particular points when you have to change the boundary, like the equation for the boundary. And there is a subset of this map. That's when your tree, the root of your tree is part of the tip set. So there is at least one path that goes to 0. So when that happens, your tree is root connected, and that means that the 3 pieces, in this case, if it's a ternary tree, the 3 pieces are connected at 1. So you can define the map where all the parameters that are giving you a tip set that are it's contained, 0 is contained in this tip set, then it's black. So that happens for all these black regions, and the elements when you take them, for example, this one, you get this symptotic similarity in a way that it happens also with the Mandelbrot set, but here we're not seeing like period doubling. The behavior is very simple. The maps that are generating these self-similar sets are linear, but still we have this interesting and rich topological structure for the different pieces. And so you can like have the map for the points that are at 0, but because the theorem I was telling you, one is also contained in the tip set. So if you look for all the parameters that are giving you a root connected tree, then it's the same. But now you can like ask different lambda values. So I'm going to show you the animation for that. So you're asking different lambda values, and if it's in that lambda value, then you color in black at that point. So that's the animation I did for studying that, and because of the self-similarity, the synthetic similarity between the elements and the parameter space is like giving you a hint how the different elements are going to be looking like. If you take a point in there, it's going to look similar to what you're looking at the map. So that was just one family, and just by like, for example, taking these 2 pair of T2T relations, you get a different family. It's almost the same as the last one, but now you have that the red branch, the initial red branch is always -1/2. So that's looking like that. And the parameter space is also contained in anomalous, but now your stable sets are these white regions that are contained in the boundary of these white regions are not as smooth as before. And that's some elements, some landmarks points for that boundary. And that's usually what's going to happen when you find a family and then you find the unstable set. The boundary is going to look rough, because fractals in general are rough, and that's just because of the ins and outs. When you are like trying to collide the different pieces, you can like move, and that's going to be very rough in general. So that's more a pathological case when you have this nice boundary with made out of straight lines. So that's 2 different families to compare it, but you can find other ones. That's the map that's related to the Wilferson picture I was showing at the beginning. And here the stable set in white is when you have a Cantor-like set, and the pictures, the elements are more or less like these binary trees, where you have the one branch that goes this way, and then the other one is just minus that complex number. So you have z and minus z. That's going to be the pair of numbers. But so you can like look at the internal structure when you lose this structural stability, and then you can look at these equations that I was showing you, that you have pair of relations, and the element is connected, and you have different examples in the internal structure, and that's one case when the intersection of the 2 first level pieces are intersecting, and in this case you are getting the same example at the beginning, and this corresponds to the Rousey fractal. And then you can also compute the geodesics of the boundary and do different things in these cases. So then when you lose the structural stability, the internal part is also interesting, because you can have this node-to-node connectivity and find different hierarchical structures inside the interior part. And for example, if you remove one of the branches, instead of taking one combinatorial case, and you have another family, and I'm going to picture that in red, so you can find different pieces of the unstable set. There are some famous ones from that family, and Wilferson was aware about this relation between what he was doing and the self-similar sets, but now I will have this tool that you can find families just by imposing tip-to-tip conditions. And in this case, for this example, you have this pair of relations. And I'm going to show you one family that you get for just the upper relation, and then another one for the lower relation. That's the family you get for the upper one. And this node, this branch is the parameter Z, but then the other one has to move according to the expression there. That's the other family. So when you compare these two families, you notice that there is the initial element that we had seen before, that's this element that's in common between the two families. But sometimes it provides different values when you get a special algebraic number. And in this case, this is the example that you get. That's the common element also between the two families, the upper one and the lower one. So that's the example. And in this case, you can tessellate the plane, and so we can find interesting examples just by combining different tip equivalent relations in there. Since I had only 25 minutes, I'm gonna stop sooner just to see if you have any questions. I've been also 3D printing some trees. Thank you also for the organizers for taking again this conference that was canceled last year because of COVID. And nowadays I'm working for Wolfram Research, so I'm in the private sector, but I'm happy also to be looking at what's going on in academia. And I've also been 3D printing some examples as well, because you can get some insights of these structures.
Right. Okay.
So if there's any questions, I can ask it, or just you can contact me also.
Right. Yeah. A nice and artistic taste of complex dynamics. Thank you, Bernat.
Thank you.
So time for questions, comments, and remarks.